Let's take a moment, breathe in, breathe out, let the clock tick once, let your thoughts slow down. Tonight, we're going to stretch time, not in a metaphorical sense, but in a literal, physical, real one. We're going to talk about time dilation, why time doesn't always move the same for everyone, why speed can stretch or squeeze the flow of seconds, and why, if you move fast enough, you could leave Earth, take a short trip, and come back to find that everyone you knew has aged decades. Sounds like science fiction, it's not. This is one of the most beautiful truths in physics. It starts with one strange idea. Time is not fixed, it's relative. Time does not tick the same for every observer. It bends, it warps. It flows differently depending on how fast you move or how deep you are in a gravity well. It's elastic. It is not what we were told. For most of human history, time was thought to be absolute, ticking away steadily like a god's metronome. But in 1905, a young patent clerk named Albert Einstein changed that. He didn't look like a prophet, but his thoughts would bend the structure of the universe itself. Einstein's special theory of relativity told us this: the faster you move, the slower time flows for you. At first, the world didn't believe him. It sounded absurd. But physics doesn't care about belief. It only follows the truth, even if that truth makes you dizzy. Let's rewind the clock, not just in theory, but in time itself. It's the year 1905. The world is lit by gas lamps, newspapers, and steam. But in the mind of a 26-year-old patent clerk in Bern, something electric is happening. Albert Einstein, quiet and unremarkable in appearance, is about to publish a paper that will disturb the rhythm of time itself. It's called On the Electrodynamics of Moving Bodies. Not exactly a thrilling title, but within it, a revolution. At its heart is a question. What if the speed of light is always the same, no matter how fast you ray moving? This single idea, radical at the time, leads to a consequence that defies common sense. If light must always travel at 299,792,458 meters per second, then space and time themselves must adjust to keep that speed constant. So what adjusts time? If you move faster, time must slow down for you so that light still appears to move at the same speed. It's not science fiction. It's not metaphor. It's math. It's nature. And it's been proven again and again. This is the concept of special relativity. It tells us that the laws of physics are the same in all inertial frames, and that the speed of light in a vacuum is constant regardless of your motion. From this, time dilation is born. Imagine two identical clocks. One stays on Earth. The other is put on a spacecraft and launched at incredible speed, say 90% of the speed of light. To the person inside the ship, time feels normal. Seconds pass like they always have. But when they return to Earth, they find something chilling. Their clock has ticked fewer times than the one left behind. They have aged less. By moving fast, they experience less time. They skipped ahead, not through a portal, but through velocity. This is time dilation, not in theory, but in your biology, your heartbeat, your memories. Einstein didn't just imagine this. He built it from the mathematical foundations of Hendrik Lorentz, a Dutch physicist whose equations, now called Lorentz transformations, were the scaffolding for this new space-time reality. Lorentz described how space contracts and time slows as you near the speed of light, but he didn't realize he was glimpsing a new universe. Einstein did, and in doing so, he redefined what time is. Let's imagine two people. They're twins, born on the same day in the same hospital. Their lives nearly identical until one of them leaves Earth. Not in anger, not in exile, but for an experiment. One twin boards a spacecraft, a ship capable of reaching speeds close to the speed of light. She looks back at her brother, waves, and disappears into the black. For her, the journey feels normal. Maybe she reads a book. Maybe she sleeps for a few days. To her, the trip takes only a couple of years. But when she returns to Earth, something is wrong. Her brother is not the young man she remembers. He is old. His hair is gray. His hands shake. His voice is slower now. Because while only 2 years passed for her, decades passed on Earth. They are still twins, but no longer the same. This is not science fiction. It's not a parable. It is the most famous example of time dilation and relativity. We call it the twin paradox. But is it really a paradox? It's only a paradox if you assume time is absolute, if you believe both twins should experience time the same way. But they don't, because one stayed on Earth and the other moved at relativistic speeds. That speed changed the rhythm of her time. It made her seconds longer. It stretched her hours wider. Her clock ticked slower, not broken, just different. And when she returned, the clocks reconciled, but with different answers. This thought experiment, once considered absurd, has been confirmed in real life. In 1971, physicists Joseph Happel and Richard Keating placed atomic clocks on commercial airplanes. They flew them around the Earth, eastward and westward, while identical clocks stayed behind. When the flying clocks returned, they were off. Not by much, just a few nanoseconds, but it was enough. The clocks that moved had ticked more slowly, just like Einstein predicted. And now, every time you use your phone, every time you check your location with GPS, you rely on time dilation corrections, because the satellites orbiting above us move fast enough and far enough from Earth's gravity that their clocks would drift by kilometers each day if we didn't account for relativity. Time is not constant. It is not fair. It is not universal. It is curved, bent by motion, twisted by speed. And in that curve, we find not just math, but something strangely human. The idea that you and I could experience time differently just because we move differently makes the universe feel both vast and deeply intimate. The speed of light, 299,792,458 meters per second, a number so specific, so sharp, it doesn't even feel real. It's not just fast, it's the speed limit of the universe. Nothing can move faster, not you, not a rocket, not even a thought, but it's more than a number. It's a cosmic truth, a law not of speed, but of structure. Because here's the strange part, no matter how fast you're moving, light always appears to travel at the same speed. It doesn't matter if you're standing still, racing in a car, or flying through space at 99% the speed of light. When you measure light, you always get the same result. This breaks reality as we know it. To make this possible, the universe compensates. It adjusts the only things it can, space and time. If the speed of light must remain constant, then time must bend. This is the origin of time dilation, not because time wants to slow down, but because it has to protect the speed of light. It's a beautiful paradox. The faster you move, the more the universe warps time around you to keep light's sacred speed intact. But what if you could reach the speed of light? What would happen? Physics tells us you can't. Not if you have mass, but hypothetically, if you did, time would stop completely. You wouldn't age. You wouldn't move forward in time. You would become frozen, not in space, but in experience. You would exist in a single moment forever. Time dilation wouldn't just stretch seconds, it would annihilate them. This isn't fantasy. This is how light itself experiences time, from the photon's perspective. Traveling from a distant star to your eye, there is no time. Its entire journey happens in an instant. Billions of years of cosmic travel experiences now. Light doesn't age. It doesn't perceive change. It just exists, timeless, and so the more you approach light speed, the more you become like light, slower, stretched, unchanging, not because time is failing, but because it's doing exactly what it was meant to do. Up until now, we've talked about time dilation caused by motion. By moving fast, really fast, time bends, slows, and drags behind. But what if you're not moving at all? What if you're standing perfectly still, yet time still treats you differently? Welcome to the other half of the equation. Welcome to gravitational time dilation. It starts with a question Einstein asked himself in 1907. What happens to time in a gravitational field? He imagined a man falling freely from a rooftop. During his fall, the man would feel weightless, just like an astronaut in orbit. This thought, this simple picture, led Einstein to one of the most profound insights in physics. Gravity isn't just a force. It's a warping of space-time itself. And where space-time curves, time slows down. This is general relativity, Einstein's theory from 1915. It tells us that massive objects, stars, planets, black holes, don't just sit in space. They bend it, like a heavy ball on a stretched rubber sheet. Space curves, and time curves with it. The deeper you are in a gravitational well, the slower time passes for you. Think of a clock at sea level and another clock at the top of a mountain. The mountain clock ticks slightly faster, not by much, just nanoseconds, but it's real, measurable. We've tested this with atomic clocks on airplanes, mountaintops, satellites. Time flows differently depending on altitude. You and someone on the International Space Station are aging at slightly different rates because gravity stretches time, even when you're standing still. Now, stretch this concept further. Imagine a neutron star, a remnant of a massive explosion, so dense, so compact that a single teaspoon of it would weigh billions of tons. Stand on its surface if you could, and your time would slow dramatically compared to someone in open space. Now imagine a black hole, the ultimate time dilator, a place where gravity curves space-time so deeply that even light can't escape. Get close to the event horizon, the edge, and time begins to crawl. To someone watching from far away, you appear to freeze, suspended in a moment. You don't feel anything unusual, but to the outside world, you are lost in time, forever falling, never arriving. This isn't poetry, this is physics, and it has consequences. Black holes slow time, mass slows time, even the Earth gently slows time. Right now, your feet are slightly deeper in Earth's gravity well than your head, so technically, your toes are aging more slowly than your scalp. Yes, even your body experiences time unequally, and somehow that makes it all feel more fragile, more beautiful, because time isn't a fixed drumbeat we all march to. It's a living rhythm, soft, flexible, curved by stars in motion and mass. You are not bound to the same time as the person next to you, and that is kind of lonely and kind of perfect. So far, we've talked about space travel, twins, and event horizons, but you're probably not a starship pilot or a falling astronaut. You're just here, listening, existing. So what does time dilation mean for people like us? For the everyday, for your morning coffee, your phone, your location on a map. It turns out you live with time dilation every single day. Let's start with GPS. Those little blue dots on your phone don't just magically appear. They're calculated with signals from satellites orbiting high above Earth, around 20,000 kilometers up. These satellites carry atomic clocks so precise they lose less than a billionth of a second per day. But here's the catch. Those clocks are moving fast, thousands of kilometers per hour, and they're far from Earth's gravity well, which means they're experiencing both types of time dilation. From motion, special relativity. From altitude, general relativity. Without correcting for these effects, your GPS location would be off by up to 10 kilometers every day. The map would lie, the roads would vanish, reality would bend the wrong way. But because we understand relativity, because we know how time bends, we correct the clocks. And so, you find your way. Think about that. Right now, as you listen, dozens of satellites are whispering down to Earth, adjusting their clocks so you can find your house, your coffee shop, your sense of where you are. Einstein lives inside your phone. His ideas aren't distant. They're quietly woven into your reality. But it doesn't end there. Even here on the surface of Earth, your body is experiencing tiny differences in time every day. If you live on a mountain, you are aging slightly faster than someone at sea level. If you fly frequently, you're experiencing time marginally slower than someone who stays on the ground. Over your lifetime, the differences are barely noticeable, just a few microseconds. But they're there. The math is real. The universe keeps score, and it makes you wonder if time is flowing differently in every corner of space, in every motion, in every orbit. Then what is now? Is there even such a thing as a shared present moment? Or are we all sliding through our own slices of time, forever a little out of sync, even as we sit in the same room, speak the same words, and fall asleep to the same video? We are never quite in the same moment, and somehow that's okay. Let's not rush into this moment. Let's let it arrive, like a planet curling slowly around its star. Let the seconds stretch just a little longer, because that's what time does when it's asked politely. It bends, it listens, it slows down for those willing to move fast enough to notice. Imagine just for a moment that you're light, not a metaphor, not enlightened, just a photon, a particle of pure energy. You were born in the belly of a star, shot across galaxies to people, separated by vast space, say one orbiting Saturn. One walking her dog on Earth do not agree on what events are happening at the same time. Relativity destroys simultaneity. It says that now is relative, which means your present moment isn't the same as mine. The answer isn't motion or gravity. It's entropy. The second law of thermodynamics tells us that systems tend to move from order to disorder, from low entropy to high. Time dilation tells us the universe doesn't tick like a clock. It flows like a river that changes speed depending on the current beneath your feet. You're not floating in a sea of identical seconds. You are moving through your own stream. It's okay if it flows differently than someone else's. That difference is the gift, because time, with all its bends and stretches, makes every life a unique song. Not better, not worse, just yours. It's why a broken glass doesn't unbreak, why smoke doesn't return to the match. Entropy defines the arrow of time. It points us forward. Either way, the universe still spins, still bends, still waits for no one. But time dilation suggests that this arrow isn't fixed and curved. Space-time near black holes or at extreme speeds, the arrow twists. It still flows one way, but its length changes, its tempo slows, it's still forward. But sometimes, barely, your now is bent, twisted, delayed by your motion, your location, your gravity. We overlap only briefly, and even then, just an illusion. We live in time bubbles, spheres of experience, and no two are perfectly aligned. It's lonely and liberating. Past ancient dust, collapsed giants, exoplanets teeming with maybe life. Strip away the stars, the satellites, the space-time diagrams. Ask yourself, what is time? To your body, time is change. A cell dividing, a wrinkle forming, a memory being stored. To your brain, time is memory, a before, a now, and an after. Time dilation, real, measurable, tells us that even those fundamental pieces of self can drift. Your memories could be younger than mine. Your body might age more slowly if your life involves motion. Pilots, astronauts, even long-distance travelers experience it tiny, but present. You could live a little longer just by moving more. And now, you reach an eye on Earth, and a brain wondering what time even is. How long did it take you to get here? Billions of years, we say, but you don't experience time at all. From your perspective, your birth and your arrival happen in the same instant. It is the aching beauty of knowing that someone far away is living a different second than you are. It's the heartbreak of astronauts returning to a planet that moved on. It's the soft terror of being near a black hole where time outside rips forward while you're trapped in a frozen moment. It's the calm peace, the bedtime comfort of knowing that time isn't cruel. It's just elastic and deeply honest. No waiting, no journey dot just now, because at the speed of light, time stops. It doesn't crawl, it doesn't lag, it ceases to exist. This is not an idea, it is a measurement. It is what the equations of special relativity insist upon with no apology. Down here on Earth, we've seen this magic happen in the vast circular tunnels beneath Switzerland. Scientists fire muons, tiny subatomic particles at near light speed. Muons are unstable. You board a ship, not a noisy rocket, but a silent, smooth craft. Engineered by the descendants of physicists and poets, you accelerate, slowly at first, then faster, faster still. 0.9 times the speed of light. Time for you slows down dramatically. When your onboard feels like 7 on Earth, you send a message home. They reply, but by the time you receive it, the sender is older than they were when they typed it. You keep going. At 0.99 C, every second for you becomes nearly infinite for those on Earth. The stars blur, galaxies smear, and back home, people age, nations fall, languages vanish, cities dissolve into dust. To you, it's been 5 years. To Earth, thousands. You come back. The planet you knew is gone. You are a traveler, not just through distance, but through time itself. They decay in microseconds. They shouldn't live long enough to be detected, but when they're moving fast enough, they do. Their internal clocks tick slower. To them, time seems normal, but to us, they live longer, not because they changed, but because their velocity changed the rate at which they experience reality. It's not just poetic, it's predictive. It works every time. The universe listens to speed. Let's say you're an explorer, not of land or sea, but of time itself. There's no such thing as a universal now. Let's get personal for a moment. So what gives time its direction? Why does it only move forward? And here's something physics textbooks won't say, but you'll feel it anyway. Time dilation is emotional. Let's go to the places we didn't go before, from the subtle shifts in space, from the overlooked seconds between ticks, from the minds who first dared to question what time really is. Because time doesn't reveal itself all at once, it peels back slowly like a curtain, or a nebula unfolding under starlight. Before Einstein made time famous, there were others, quieter voices whose ideas formed the backbone of what we now call relativity. One of them was Ole Rømer, a Danish astronomer in the 1600s. He didn't know he was laying the groundwork for Einstein. He was simply following the math. At rest, the beam moves vertically, but when the clock is in motion, the beam takes a diagonal path, meaning it travels a longer distance between ticks. In 1976, the Vesseleveen rocket experiment launched a hydrogen maser clock into space. As it ascended, it escaped some of Earth's gravitational grip, and it ticked faster. Not by much, but enough to match Einstein's predictions. The moment you're experiencing right now is not the same as someone moving quickly past you. The other travels to a distant star at near light speed and returns. The traveling twin has aged less. Their clock ticks slower, their muscles sag slower, their hair turned gray slower. The earthbound twin is older now, not by illusion, not by mistake, but by physics. We've tested this with atomic clocks flown on airplanes. It's real. Hair paused, forever falling, never quite arriving. This is time dilation literally, because time is not a shared blanket. It's a personal stream, even if you were born at the same time under the same stars. You could age differently, not metaphorically. Time, they confirmed, is not constant. It's shaped by speed and gravity. It listens to where you are and how fast you move. Since light speed cannot change, the only thing that can change is time. The event horizon, time slows to a crawl for the falling observer from the outside. They appear frozen, suspended at the edge of eternity. But for them, time flows normally. They feel no delay. Their heartbeat continues. Their thoughts move, but to the universe outside, at its most extreme, a cosmic edge where time itself warps into something unrecognizable. The ticks must slow down. Time must dilate. It's not just theory, it's geometry, simple, elegant, inevitable. Alongside him, George Fitzgerald proposed that moving bodies might actually shorten in the direction of motion, a radical thought that danced with the idea that space and time were more flexible than we believed. He noticed something odd. The moons of Jupiter were arriving late. Not always, just sometimes. But even he, with all his genius, stood on the shoulders of these lesser-known giants. When Einstein's equations told him that time slows down for moving observers, he listened, and the universe echoed back in experiments in particle collisions. In muons that lived longer than they should, he concluded light must have a speed, and it wasn't infinite. It took time for light to travel across space. This simple observation was the first ripple in a still pond, a moment that would eventually cascade into the realization that time is not fixed. And there was Lorentz, whose transformation equations, now called Lorentz transformations, mathematically describe how objects contract and time dilates at high speeds. Einstein took these fragments and wove them into something more, a tapestry of ideas where time became relative, elastic, and personal. You can talk about time dilation without talking about the famous light clock, beam of light bouncing between two mirrors. This same logic has been tested. Let's drift further, to black holes, the deepest time wells in the universe. Now step back. Think about this. There is no universal now, no shared present. This leads us to the twin paradox, a thought experiment turned reality. Imagine two twins. One remains on Earth. The other travels to a distant star at near light speed and returns. The traveling twin has aged less. Their clock ticks slower. Their muscles sag slower. Their hair turned gray slower. The earthbound twin is older now if two people live the same number of seconds. But when seconds are stretched, are their lives longer? Just slower. If you could stretch time by moving fast enough, could you live forever? Not from your own point of view, but maybe from someone else's, not by illusion. Not by mistake, but by physics. Your experience of time is uniquely yours, shaped by your speed, your gravity, your motion through space. Your heart beats, your cells divide, your thoughts wander forward. You feel time. Regardless of how it bends, the block universe theory suggests that past, present, and future all exist simultaneously. GPS satellites orbit Earth at high speed and high altitude. Without correcting for time dilation, both special and general, their navigation would drift by kilometers each day. Every time you check a map, you're depending on relativity every step, every direction. Grounded in Einstein's insight, we are not moving through time. We are simply experiencing one slice of a four-dimensional whole. Your future already exists. Your past is still there. The emotional dimension of time, to know that someone far away, truly far, is aging slower than you. To imagine astronauts orbiting Earth, their time a few microseconds behind. To think of a future where we send humans on interstellar missions only to return and find everyone they knew gone. Not because of tragedy, just because of motion. You are a traveler, not through moments, but through slices. Your journey is not a line, it's a path through a static landscape of events. It is a philosophical mirror. It forces us to ask what it means to live in time, to age. To forget, to hope. We stretch it, bend it, spend it, but it was never truly ours. We've tested this with atomic clocks flown on airplanes. It's real. They are paused, forever falling, never quite arriving. This is time dilation, literally, because time is not a shared blanket, it's a personal stream. But what does that mean for memory, for experience? Cause and effect blur. Physics breaks down. This is the edge of our understanding. The quantum foam where space-time flickers, uncertain and undefined. Some theorists speculate time may not be continuous, but discrete, made of tiny indivisible moments like frames in a cosmic film. If true, time dilation might not stretch time, but slow the switching of these frames. A deeper kind of delay. And this, perhaps, is the quiet beauty of time dilation. It humbles you. It reminds you that your clock isn't the clock. There's more, deeper still. Some physicists argue time may not even be real, at least not in the way we experience it. Is that comforting or unsettling? Perhaps both. The Planck time, the smallest measurable unit of time, is around T-40 for seconds. Below this, we suspect time loses meaning. And yet, even in the strange, pixelated cosmos, your body lives in rhythm. Time dilation is not just for physicists. It's written into the fabric of your life. But beyond the math, the experiments, the equations, there is emotion. Motion is a kind of goodbye. Time dilation, then, is not just a scientific fact. And maybe it is the deepest reminder that we do not own time. We only borrow it. Still, it flows. Still, it whispers. And still, it waits for no one. Let's slow everything down now. Slower than clocks. Slower than seconds. Slower than thought. Let the math fade. Let the diagrams dissolve. Let the mind rest inside the idea. Time is not a universal truth. It's not a perfect ticking ruler shared by all. It's local. It's personal. It's shaped by where you are, how fast you're moving, and how much gravity wraps around you. Every second is relative. Every heartbeat, a slightly different beat. You and I, we're not in sync. Not fully, not ever. Even in this moment, as my voice reaches you, your version of time is ever so slightly your own. The universe is no master clock. Only rhythms. Only differences. It's beautiful and a little sad. One day, billions of years from now, as stars fade out and galaxies drift away, the universe will approach a final moment. Not a bang, not a collapse, but a stillness. A place where energy is gone, heat is balanced, motion ends. A moment where time has nothing left to measure. That moment is called the heat death of the universe. A strange kind of death where nothing explodes and everything just stops. A place beyond clocks, beyond before and after. Just quiet, just time without time. But for now, you are here, alive, breathing, moving slowly even if you don't notice it. Your atoms dance to the rhythm of a planet in orbit. Your mind drifts across the waves of curved space. And whether you're asleep or quietly awake, you've just traveled through something incredible. You've bent time with nothing but your attention. You'll either learn something or fall asleep. Either way, I did my job. This was CortexFlare, where the universe whispers softly, good night.